Welcome to The Explainer. Today, we're diving into something absolutely crucial for anyone building production-grade AI search pipelines. Listen, if you've ever built an AI agent that seemed, perfectly intelligent at first, only to just completely fall apart a few months later, you're gonna love what we uncover today. Most RAG systems work flawlessly in the demo and silently fail in production. That provocative quote from Digital Applied really hits the nail on the head. It's kind of the dirty secret of the AI industry right now. These Retrieval-Augmented Generation systems, our RAG systems, they degrade silently. There are no crash reports, no flashing red lights, no error logs. They just quietly start giving your users worse and worse answers.
So here is our roadmap for today. We're going to cover why production RAG fails, the multi-stage search funnel, hybrid retrieval in RankFusion, the cross-encoder re-ranker, the document drowning paradox, and we'll wrap up with rules for production scale. Let's jump in. Part 1. Why production RAG fails.
Okay, the most important thing to realize here is that production RAG failure is usually an engineering discipline problem. It's not a vector database issue. We're dealing with specific, silent anti-patterns. Things like your text chunks being too big. Maybe you're retrieving way too few candidates at the start. We're completely ignoring the re-ranking stage. And then there's missing provenance, meaning broken or missing citations and using stale embeddings. The crazy part? None of these trigger an error code. They don't crash your server. They just quietly serve up slightly worse answers every single day, slowly destroying the quality of the whole shebang.
Section 2. The multi-stage search funnel. To actually fix these silent degradations, we have to completely move away from single-stage search. Think of it like a funnel. When you're searching massive unstructured datasets, you're always balancing computational cost against ranking precision. You literally cannot run a highly expressive, token-level model over millions of documents at inference time. It's computationally intractable. So we use this multi-stage approach. Step 1 is all about cheap, broad candidate generation so we don't miss anything. Step 2 applies really fast metadata filters. Step 3 brings in the heavy lifter, the cross-encoder, to re-rank that smaller pool of candidates. And finally, Step 4 uses an LLM to validate those final few answers.
To really get why this funnel works, we need to look at the models driving it. At the top of the funnel, we use bi-encoders. These compress text into static vectors, embedding the queries and the documents totally independently. They are lightning fast and absolutely great for broad recall. But down at the bottom of the funnel, we shift over to cross-encoders. Now these are computationally heavy and slow, because they process the query and the document concatenated together as a single sequence. This gives us full cross-attention across all tokens. It prioritizes absolute precision, catching all those complex semantic dependencies that single vectors just completely miss.
Moving on to Part 3, Hybrid Retrieval and RankFusion.
Right at the very first stage, we run into a major issue known as a modality mismatch. If you rely purely on dense semantic vectors, sure, you'll capture the conceptual intent of a query, but you are going to completely miss exact identifiers. Part numbers, regulatory code, specific names, poof, gone. But if you rely purely on sparse BM25 keyword search, you'll nail those exact identifiers, but you'll totally miss the semantic intent when a user asks a question using different words than what's in your text.
So the solution is actually pretty elegant. Run both in parallel and merge them. Enter reciprocal rank fusion, or RRF. This is the magic algorithm that marries our dense semantic retrievers with our sparse keyword retrievers. And what's really fantastic here is that it's an unsupervised algorithm. It takes those incomparable absolute scores from the different models and converts them into standardized, rank-based scores using a super simple formula. 1/60 plus the rank. No expensive training data or labeled queries required. It's brilliant!
And the impact of this? It's massive. When you implement this simple hybrid approach using RRF, you're looking at a 10 to 20% recall lift on entity-heavy queries. If your data has any meaningful entity surface, like product codes, model numbers, or names, and you are just running pure vector search, you are literally leaving a massive performance lift on the floor.
Section 4. The cross-encoder re-ranker.
So we reached the climax of our funnel. But is the heavy compute cost of a re-ranker actually worth the latency? Well, the benchmark data for complex multi-hop queries proves that it absolutely is. Look at this. A baseline Raptor hierarchical setup hits 62.5%. But the exact moment you slap a Cohere cross-encoder re-ranker on top of it, boom, performance jumps to 71.8%. That is a 9.3% absolute boost. So the takeaway here is, yes, for sure, the neural re-ranker is empirically the single most impactful modular addition you can make to your entire pipeline.
Which brings us to part 5, the document drowning paradox.
Now you might be wondering, and it's a perfectly logical question, if these cross-encoders are so precise and intelligent, why do we filter the candidates down so aggressively early on? Why not just hand the re-ranker 1,000 documents and let it find the perfect answer?
Well, welcome to the drowning in documents paradox. Giving the re-ranker too much data actually destroys its accuracy. First, you get what's called attention dilution. Basically, as the context window fills up with irrelevant documents, the mathematical weight of the model's attention just gets spread way too thin, and it loses focus on the correct chunk. Second, you get phantom hits. Pointwise cross-encoders evaluate pairs independently. When you feed them hundreds of unrelated documents, the out-of-distribution noise from the long tail of your data actually tricks the model. It starts assigning high scores to complete false positives. No way around it, you have to keep the candidate pool tight.
Finally, Section 6. Rules for production scale. Let's get into some actionable rules. Rule number 1, your chunk size. You want to aim for 500 to 800 tokens with a 50-token overlap. That is the absolute ideal sweet spot for pros to preserve contextual continuity. If you use those massive 1,500-token defaults you see in a lot of basic tutorials, you're just going to drown your model in surrounding noise and totally dilute your semantic retrieval signal.
Rule number 2 is your retrieval candidate count. 12 to 20 is the default count you need at the top of the funnel before re-ranking. The standard default of 3? That's really only good for super simple lookups. If you want multi-hop and synthesis queries to actually work, you have to over-retrieve at that first stage. Because think about it. If the retriever fails to capture a relevant document early on, the re-ranking stage cannot magically recover it. It's just gone.
Rule number 3 is all about saving on compute costs and reducing latency. You don't always need to run the re-ranker. Adaptive re-ranking decision systems, or ARDS, act as an intelligent router. If the first stage retriever finds a top candidate with a score that is massively separated from the rest of the pool, meaning it's a completely unambiguous match, ARDS just bypasses that expensive cross-encoder entirely and routes the answers straight to the user. It's a real game changer for efficiency.
And rule number 4, provenance. Guys, provenance is roughly 80% of perceived user quality. Your inline citations absolutely must resolve to actual retrieved source chunks. Without strict provenance and verifiable citations, your AI is going to confidently hallucinate, and you will destroy user trust faster than literally any other failure mode on this list.
So I want to leave you with this final thought. Your demo might work flawlessly today, but without multi-stage retrieval, what happens to your users' trust tomorrow? When your data scales up and the queries get way more complex, is your system going to adapt, or will it silently fail? Thank you for exploring the depths of AI retrieval architectures with us on this explainer. Keep building, keep learning, and we'll see you next time.